Okay, I thought we'd take just a quick dive through some proofs involving similarity. So we need to start with the three new postulates and theorems we've learned to help us prove similarity. So the first one being if you have two angles that match, your triangles are similar. And of course, this does also mean that that third angle is congruent too. So it's really the angle, angle, angle postulate. And that's really just almost a definition of what a similar triangle is. Um, Down here we have SSS similarity, and it's different from SSS because now the sides are just required to be proportional and not congruent. So this little squiggle sign you can imagine, it's for similarity, but it means proportional. What's proportional? Well, if this was a 5, and then a 4, and then a 7, and this magically became this, we would know that those sides are in proportion because they have a common scale factor. You multiply one to get the other by multiplying by 2, right? So being proportional, which is having this sort of relationship here where two equal ratios, it's really no different than having a scale factor. And I find the scale factor is easier to work with. Um, and over here you have a scale factor between two of your sides. So say this is 6 and 8, and this is, I don't know, double it again. Those would be proportional sides. And if you have that angle in the middle, you can substitute that for a side, and you have SAS, similarity. So let's do some proofs then. So we're likely going to see one of those new statements down here, right? And what we're trying to prove is that these two triangles are similar. Okay. So first of all, we're given some parallel lines and some right angles. And since we're going back to looking at A's and S's, it's important to state exactly when two angles are equal. And being given that M and N are right angles, that should mean that they're equal to each other, right? They're both right angles. Call that all right angles are congruent. And if we look at the rest of this, maybe there's another angle we could find, because I don't have much information about the sides, right? But the angles, maybe so. Okay. Let's take a look at angle MRS. Where is MRS? Right here. So this angle right there. Now, if we look at this angle also here, and we see that we have these parallel lines, these angles right here are one of our angle pairs. They're corresponding, okay? So angle MRS is congruent to angle NST. Those two I labeled in the picture, and that's because of the corresponding angle theorem. Okay, a big one here. And the final statement is going to be figured out based on, well, what do you have? What are your tools? You got an angle, got another angle. So those two triangles here, this one and this one, they both have two pairs of equal angles. So this would be angle-angle similarity, and those triangles are similar. Not congruent, but at least they're similar. So let's keep going here. So we're really kind of obsessed for these proofs to try and get a proportional relationship written, despite whatever they give us. So one strategy to start this proof, which is basically telling us that these lengths here are about 3/4 of the size of the whole length from P to R or P to S. So if we can convert that into some sort of scale factor, we probably could make some progress here. So what we'll do is a scale factor is a ratio of sides. So I want to divide both of them. Basically just move around some terms by dividing, and we get this. How did I do that? Well, the division POE. Okay. And why am I doing this? Why am I moving around these ratios? Well, because now we have a statement that says that these two ratios are equal to each other, no? Because they're both equal to 3 over 4. And when that happens, when the ratio is equal to 3 over 4 and 3 over 4 is equal to the ratio, then those two ratios are equal. That's the transitive property. You could also say substitution, but the transitive property is more precise. Great, so with this statement, we have two sides that are proportional. So we can, two s's count there. So it looks like to finish this up, we're going to either need a or another proportional side. And I see the a here. So 4's got to be something about an angle we've overlooked. And because we're interested in these two sides here, it's likely going to be the included angle here at P. So if I say angle P is congruent to angle P, that is a quick way by the reflexive property. Remember, reflexive means looking back at itself as an equal. And what do you know? That means that these triangles are congruent. No, sorry. These triangles are similar, of course, right? But it can be tricky, right? But whenever we have these sort of ratios involved, we're probably shooting towards similarity. Whereas when we did it with side lengths and congruent sides, that would have been maybe SAS. But this will do. Okay, and the more interesting one here, more challenging. So we have some bisects that are happening, and I can start putting in little markings, because if A is getting bisecting, I'm losing my, there's a lot of letters here. B gets bisected, or rather B does the bisecting, and AB, and this. Okay, got it. So what's the definition of bisect then? Let's see. Because with this first block in 2, naturally we're going to try and look for using this and this and converting it normally into some sort of equation. So I think one way we can get use of this, and I'm looking over here too, maybe if I wrote out what bisect meant using 1/2, so like JA is 1/2 JK, the part is half the whole, and also JB is 1/2 JL. And then if we do that division, like before, we would start getting more ratios like the given. In fact, look at that. We have not 1, not 2, but 3 different ratios, which are really scale factors. We've basically identified 3 times all 3 sides, so that should hint towards SSS. All of them have the scale factor of 1/2 if they're going in the right direction. And this is put together again by the transitive property. And finally, and we'll talk a little bit about this on the picture as well, because the picture is really what makes this pretty tough. But side similarity is what this screams right here. 3 proportional sides, 3 ratios, all of them in proportion set equal to each other. So what were the triangles we were trying to show? It could be a little bit. We had this big one, and then jab was just this one. Okay. So we basically found out that um, all of the lengths of the blue triangle had been scaled by a factor of 1/2, and that was the argument to show that